because in deep learning, frequently you don't see model classes, at least explicitly discussed. Sometimes you do, sometimes you don't. Another issue, a mathematician would say, well, please tell me how we're going to evaluate algorithms at the end of the day. If I come up with this clever algorithm and I think it's a great way to recover this f, that is to create this function f hat, how are we going to decide whether I did a good job? And in mathematics, we like to do this via some norm. And so that's what I'll assume, that there is assigned to me a norm, how we're going to measure the error after I've created f hat. Namely, I'll look at the deviation between f and what I've created in f hat. And I'm going to assume that this norm is a Hilbert space norm, although whatever I say can be carried out in a general Banach space norm. And you can look at this paper here to see how that's done. The data I'm going to assume are given by linear functionals applied to f. So it's linear data. And so what do I know about f? The totality of information I know about f is that it's in this model class K and that it satisfies the data. So I let KW be the collection of all functions in K which satisfies the data. That is all I know about f. It could be any function in KW as far as the information that was given to me. Well, given the setting, there is actually mathematically a very easy description of the best recovery that you can make. That is the best approximation, f hat, you can give to f, given that f is any one of these functions in KW. And it's most easily explained by a graphic here. So let's let KW be this blue set. So the blue set here in this graphic indicates all functions. So this is in my Hilbert space, all functions that satisfy the data and lie in K. So this is the set KW. The best I could, that's all I know about f. So the best I could do to approximate f is to take the center of the smallest ball that contains KW. This is called the Chebyshev ball, and its center is Chebyshev center, and the radius is the Chebyshev radius. And that's the best error you could ever attain, and the best algorithm would take your data and find U star. How to do that numerically is a big issue, but that would be, if you could achieve that, be the best algorithm. In reality, this is a very hard problem to find U star, and we do surrogates to that problem. And we would be happy if we found any point close to this ball. In particular, if we found any point in the ball, we would know we were within a factor 2 of the best performance, and that would be satisfactory to us. Okay, so there is an optimal solution, and the optimal error you would get is this R star of R of KW, the radius of this ball. Hopefully everybody followed that. All right, now let's try to understand, what does the data give? What does the data tell me? Since I'm operating in a Hilbert space, the data are linear functionals in the Hilbert space, and so there's something in mathematics called the Riesz representer theorem that says every linear functional is the inner product with an element omega j from the Hilbert space. These are called the Riesz representers of this data functionals. So I could take these omega j's, which ostensibly would be known to me. For example, if you think about point evaluation, you may think of the delta function as the omega j. I can form the span of the omega j's. This is a subspace of my Hilbert space. And the information I get from the data, it tells me what the projection of f is onto this finite dimensional space W. So it gives me the projection of F onto W, which we denote by PW of F. What I don't know is how F looks away from the data. And that mathematically is we don't know the component of F in the direction of the orthogonal complement of W, called W perp. And what we want to do is we want to use our knowledge about F to predict what PW perp of F is. So that is in essence the problem. What is F off of the data? What does F look like in this W perp direction? There's a simple graphic to explain here what's going on. In this graphic, there's a blue blob here, a three-dimensional blob. I mean, the graphic is in 3D, so it's not very illustrative of the high-dimensional problem. But the blue blob is my set K, right? That's my model class. I know F is in the blue region here. What does KW tell me? It tells me that there is in general, hyperplane cutting through this blue blob. In my 3D example, this is just a line segment. These are all functions. If you extended the line off to infinity in both directions, this would be all functions that satisfy the data. And what I know is that F is on this line segment, on this line, but I also know it's in K, in the model class K, so I actually know it's on the line segment that enters K and then exits K. And so F is any point on this line segment. And as we already discussed, the best we could do to recover would be sort of to take the midpoint of the line segment in this case. Okay, so that's our problem, to find what is the component of F in this W perp direction. Now so you would say at this stage, well, it's a lot of mathematical nonsense. It doesn't tell me a mathematical algorithm or a numerical algorithm to actually do the job. How do I find the center of this Chebyshev ball? So let us now entertain what are possible numerical algorithms. Of course, the best and most commonly used is least squares. What would you do in least squares? You would find a space sigma here, a finite dimensional, typically a finite dimensional linear space, and try to solve this problem. Look at all functions in this linear space and find one that's close to satisfying the data. And in the old days, we always took the dimension of the space smaller than M. Our rationale was we didn't want to fit noise if we had noisy data and various things. So we took the dimension to be less than M. In current deep learning, one typically takes N a lot bigger than M, over parameterized deep learning, right? And moreover, you don't take sigma to be a linear space, you take it to be a nonlinear manifold. So the typical setting in deep learning is to take a nonlinear manifold with a number of parameters much larger than the number of data points. So here now you're going to have non-uniqueness. And so which of the functions, you're going to have many functions that are going to give you error 0 here. So which of those functions are you going to pick? That would be, to me, the question to ask somebody in deep learning. What function are you choosing if you're using over-parameterized manifolds? Which function are you choosing to fit the data? I know I can fit the data exactly. Which guy are you going to choose? So I'd like to understand what's going on there. Now, if you think, first I want to tell you that least squares absolutely does not meet our goal. If you try to analyze least squares and say, okay, I pick a space sigma and I do least squares, can I prove anything in terms of the function that I've created, f hat, matching my goal of being a optimal or near optimal algorithm for learning in terms of giving me an error that's close to the best error I can achieve, which I discussed on the earlier slides. The answer is no. And the reason is that although you may have used this model class K in the beginning to choose your space sigma or your manifold sigma, you may say, oh, well, I'll choose a sigma that approximates the elements in K very well. So even though you've done that, after you've done that, when you do least squares, you throw away completely your knowledge that F is in K. So when you solve this problem, K is not appearing. You've only used K to select sigma. So the bottom line is least squares does not fulfill our goal. Is there a remedy? And the answer is yes. Penalized least squares will do the job. So what is penalized least squares? So let's take our model class K, and let me assume, and you can get around this, but for the moment, let me assume that this set K, this model class, which is a set of functions in the Hilbert space, I want to assume that this model class is convex and symmetric about the origin. In this case, and this is rather typical, by the way, of most model classes like Sobolev spaces, Besov classes, and Barron classes in your in deep learning and the like, are all strictly convex and symmetric about the origin. In this case, you can view K as a unit ball of a Banach space Y, which is a subspace of H. In fact, you define Y via the norm on Y is defined via K. K would be the unit ball of that norm. So if you view it in this way, then if you solve one of these two constrained optimization problems, then you would have a near optimal solution or an optimal solution. What are these constrained optimization problems? Now, they're not numerical because I'm going to look at all functions in the Hilbert space that satisfy the data, and I'll find the one which minimizes the norm of G and Y. What does that mean? That since I know that my original function F, which beget the data, was in Y, this function F lambda hat will actually be in K, will be in the model class. So this will be a function in the model class, F lambda hat, and it will satisfy the data. So it lies in that Chebyshev ball. And we know by my earlier remarks that this will then be a near optimal algorithm with a constant 2. Sometimes one prefers to put this in the lasso framework where you add the penalty term here with a parameter lambda in front, and then you can show that if you drive lambda to 0, make lambda small enough, again, you do get a optimal solution or near optimal solution to our original problem. So what does this tell me and suggest to me? It says, look here, the problem with this isn't a numerical algorithm because I have to search over all of H here. However, it tells me some information that maybe what they're doing in deep learning makes sense. Namely, since I can't do this over H, I have to take a set sigma as a surrogate for H, and I'll take a linear or a nonlinear manifold as my surrogate for H, and I would like that manifold to be bigger and bigger and bigger. That is, I'd like to do over-parameterized, solve an over-parameterized problem, because this will get me closer and closer to having, to emulating H in this minimization problem. So this simple exercise tells me, well, these guys aren't so stupid. Maybe it makes sense to solve a over-parameterized learning problem. And the fact that they don't necessarily regularize, that is, inject K into the picture, this suggests to me that, well, I need to inject K into the picture, but in the lasso formulation, it can be in a very weak form because it's only when lambda tends to 0 that I get the optimal solution. So I hope at this stage people have see some of the motivation for what they're doing in deep learning. Okay, now let's talk about actual numerical algorithms. That was a pseudo numerical algorithm because I had to search over all of H, which we can't do. So what we do in reality is we replace H by a linear or nonlinear space sigma, and we solve the corresponding problem, not where we minimize over all of H, but over sigma. Now, of course, we're going to incur some error. The bigger we can take sigma, the finer the space sigma is, the better we're going to do. And one can give, in fact, a quantitative estimate. I don't want to get into it too deeply, but you can give an estimate that tells you how close you are to actually giving an optimal solution to the learning problem. And it depends on how well sigma or how nice sigma is at filling up H, as measured by the distance of your model class to sigma in this Y norm. Okay, so let's now talk about what a typical, so this tells me a numerical strategy for solving the learning problem that I can prove it will give me a near optimal solution. Let's now talk about what deep learning does. How difficult this solving this numerical problem is I haven't discussed. This is a very difficult problem in high dimensions to do, but I haven't discussed that yet. But let's see what a typical learning algorithm does. So what does a deep learning algorithm do? It takes its data and it divides it into two sets, a training set and a test set. It takes, for sigma, remember I said you want a good space sigma to approximate your model class. It takes sigma as a highly overparameterized neural network. So it uses neural networks, and it uses neural networks with a lot of parameters, many more parameters than the number of data. Okay? It then prescribes a loss, could be the square loss that I mentioned before, or it may have a square loss with a penalty. Typically, there is no penalty. And it goes and tries to solve minimize the empirical loss over this class sigma, right? So that's what the deep learning algorithm is attempting to do. It does this by starting with an initial guess for the parameters of the neural network, and then utilizes either gradient descent or some relative to gradient descent, such as stochastic gradient descent, to update the parameter choice. How it implements this gradient descent is a real issue. There's something called the learning rate, which tells you the step sizes you're going to utilize in gradient descent. And there is, in my reading, I don't see too explicitly the stopping criteria. How do you decide when to stop when you're doing the iterations of gradient descent? And at the end of the day, after they create their F hat using the technology I just described, they evaluate performance on the test data by something called generalization error. We're going to get into this in a moment, what generalization error is, put this on the side for the moment. But the important thing is they don't certify the performance of their algorithm in a mathematical sense of an error estimate. They instead look at an empirical quantity, namely this generalization error, which is seeing how well the F hat they created performed on the test data. Okay, so my initial reaction to this way of doing things is the following. I'm bothered by the fact that there's not generally a model class lurking in the background in this, either in the formulation of the problem or in the analysis part of the problem. As I mentioned, if you don't have a model class, you can't prove anything. So this is a red flag to me. A second thing is there's not a precise formulation in their implementation of gradient descent in terms of the learning rate, initialization, stopping criteria, et cetera. Different people do different things. And it's not like I'm telling you that if you use this initialization, this stopping criteria, this learning rate, I guarantee certain performance. We don't see that. So the design of algorithms is, I would say, more work of art versus what one typically does in numerical analysis. Another point, which I'll say something briefly on a little later, is that there's no restriction on the computational budget. That is to say, how long do they spend offline learning F hat? How many iterations of gradient descent? How much tweaking? What do they do offline? This is contrary to what we do in numerical analysis, where we sort of say, well, we know that the more computation we do, the better. So we're interested in what is our error versus the number, the amount of computation. So the bottom line is that this world that they live in is quite different than the world of mathematics or numerical analysis, where we look for certified performance with guaranteed error estimates versus the amount of computational effort we have put forward. Okay, let me move on now. So let me talk about some of these components of deep learning. The first thing I want to talk a little bit about, and I think a lot of this conference will touch on this subject, is why do they choose neural networks as the vehicle for creating their algorithm? Well, they must think that neural nets provide a good approximation to this model class, even though they haven't explicitly told me what the model class K is. They somehow think that it provides a good approximation. And secondly, that it's somehow numerically friendly. It should be easy to implement neural nets. And so what I want to do is address these two issues. Why is it a good approximation? If so, why? And is it numerically friendly? So there are a lot of several expositions on the approximation properties of neural nets. I mentioned Alan Pincus originally. This is getting now a bit old and doesn't concentrate on the deep neural nets. It's typically a single layer neural net that it analyzes, but these other articles go into deep neural nets more deeply. Okay, so let's first take a perspective on what neural net approximation is. In neural net approximation, what we do is we prescribe an architecture for the neural net, and we prescribe an activation function sigma for the neural net. Once we do that, if we look at the functions that are created by varying the parameters, as you vary the parameters of the neural network, and let me call n the total number of parameters you're using. Deeper and wider networks would use more and more parameters, right? But the collection of functions that you produce is a nonlinear manifold, right? As you vary the parameters, you get a different function, and this is the manifold. And this manifold has a little bit of structure, namely it's a Lipschitz manifold. You can prove that if you restrict the parameters to lie in some ball in Rn, this is the set of all parameters, that this is a Lipschitz function on this ball. So again, what is Mn? Given that I've chosen the parameters A to approximate F, Mn of A would be the function that I produce. Turns out to be, if I think, for example, of ReLU activation, the function I produce will be a piecewise polynomial on a very complicated partition. And so it's a function that depends on the parameters that I've chosen. And Mn is describes what this function is as I vary the parameters A. Now, what is an approximation method? So in deep learning, you use gradient descent or stochastic gradient descent to decide what the parameters are. And so the approximation component of is how do I find, given F, how do I find the parameters for F? Okay. What deep learning does is it uses gradient descent and a loss function, et cetera, to find the parameters. But you can view the approximation process as selecting, given F, selecting the parameters. And I denote that mapping by AN. So the form of approximation that's encompassed by deep learning and neural nets is what we call manifold approximation. We're approximating not from a linear space, not by something like polynomials or splines, where we have a fixed linear space. We're approximating from a nonlinear manifold. And we have these two mappings that describe, one, what the manifold looks like, and second, how we select the parameters. So if you want to say, well, gee, neural nets are great at approximating, my first reaction would be, well, oh, I didn't know you were going to allow this general form of manifold approximation. And if you allow me to do that, let me try to understand what manifold approximation could do in general. And the bottom line is manifold approximation can be fantastic. Why? Because you know that you can find face-filling manifolds. You can find a one-parameter manifold, a manifold depending on only one parameter that fills all of K. So if you open the door to me and say you're going to use manifolds to do the approximation, I say, well, wait a minute, be cautious, because I could take a one-parameter manifold and use that for the approximation, instead of your neural nets, which use a lot of parameters. Of course, the problem is that these one-parameter manifolds are very unstable. As you search to find a good parameter, changing the parameter ever so slightly changes the function Mn of A a tremendous amount, leading to high instability. And so keep that in mind. Neural nets are opening the door for instability. We, in fact, know, this classical example of instability, that you trained a network for a classification problem of identifying what objects are in an image, and you train it, and part of the training is this image, which is correctly classified as a pig, and then you subject it to a little bit of noise. And what you find out is if you add a little bit of noise to this image, you get something that looks like exactly like your original image, and yet it's classified incorrectly. So the algorithms are very unstable. This reflects the fact that the function Mn is, although it's Lipschitz, it has a very large Lipschitz constant. So instability is an issue. Okay, now let me say a few words about neural net approximation. So, I mean, people write, there are lots of papers written on this, making claims that, well, neural nets do a great job at approximating. So do they? Well, I'll just give you my quick view of the situation. I think that Huawei will talk about results of this type. Namely, that we know that neural nets can do a better job than classical methods. First of all, it does at least as well as classical methods of approximation, by which I mean polynomials, splines, wavelets, and the like, finite element methods. Anything that those methods can do, you can prove that neural nets with the same number of parameters or the same complexity do as well. Second, you have these super performing results that say they actually do much better. For example, a lip1 function on 0, 1 can be approximated to accuracy n to the minus 2 with n parameters. This defies what we normally get in numerical analysis. Normally, we would only get n to the minus 1. And so you might look at this and say, wow, that's it. That explains why neural nets are so great. They do better than classical methods. They have this super convergence rate. In fact, you can prove super convergence in a very, very general setting. I think as Huawei will talk about super convergence for Sobolev balls and the like, but we'll see what his talk unfolds. My point is that these super convergence results, interesting, very interesting mathematically, but they have to be unstable. In fact, there are theorems that tell you they're necessarily unstable mapping. So it will be hard to find this super performing approximation. And then this is where I would say, well, if you give me unlimited time to look and search for this approximate, then maybe I can find it. Because if you put no budget on my computational time, maybe I can search over this manifold and find this great approximation. I think the real value in neural net approximation lies in the fact that there are new model classes, not the classical ones of classical smoothness like Lipschitz, Sobolev, Bessoff, but new model classes where neural nets are provably good at approximating. You're probably familiar with Barron classes, which are basically the convex Hall of the ReLU dictionary. This is actually an inflation of the Barron class a little bit. But there are other ones built on the ideas of self-similarity, fractals, iterated function systems, and the like. And I kind of feel that maybe these are the reason why neural nets are a good method to choose to build your numerical platform to do learning. That they're very robust, that they cover a lot of model classes, not only the classical model classes, but very different new model classes that might match the application you're interested in. Okay, so let me now talk a bit about data. So one question you could ask is, well, how do I know I have enough data? You know, of course, I think in many of the modern applications, they have a humongous amount of data. And so they may say, well, that's not an issue for us. But to a mathematician, we would say, well, do we have enough data? So if we have our model class and we're given m pieces of information, how well can we recover a function f in this model class from these m pieces of information? The bigger that m is, the better we can do, right? In general. So there are ways to measure how well you can do. The most famous is the Gelfand width that says that if you allow any m linear measurements, that is any m linear functionals, then it tells you if you choose these linear functionals, these data sites, as best possible for the set K, then it tells you how well you can do. So in your given setting, you'll never do better than the Galfond width. So I think it's important, my view of the subject is you need a model class, and it's important to understand what the Galfond width of the model class is to understand how much information, how many measurements M you would need to attain a certain accuracy. Delta M would tell you the accuracy, the best accuracy you could attain with M measurements. Now, of course, in learning, we typically don't have general linear functionals for measurements. We use point values, right? We have the values of function at some points, xj. So this wouldn't fit into Galfond widths exactly, because Galfond widths allow any linear functional, and here we have to use point evaluation. So you can introduce an analog of Galfond widths when you see the P on the bottom. Here, the P stands for the fact that I've restricted my measurements to be point evaluation. And delta M P would tell me the best error I could do if I could optimally choose the points x1, xm for the set K. So I know K, I now look for the best points, and delta MP would tell me the best error. And it will be worse than the Galfond width, but it would be interesting to know for a given model class, how does this behave as M tends to infinity? And then finally, you have the problem that, well, you don't get to choose the points, right? You're given the measurements. Those points have been chosen, the xj, have been chosen for you. You didn't get to choose them. So what do they do in deep learning? They say, yeah, you were given those points, but we assume that these points were a random draw from some probability distribution. And so you could say, well, all right, given a random draw, how well do you perform? And now, of course, the draw can be bad or it could be good, but you can say, okay, on average, how well do I perform? That is, for example, an expectation, what would be the best I could recover? So my point is here is it would be very useful if in deep learning, one analyze these quantities, Galfond widths, point-wise Galfond widths, and the average width to understand how much data you need to learn functions from a given model class. Okay, so if you propose a model class, I just said it, you should evaluate these quantities to understand how good your model class is, how many measurements you will need, do you break the curse of dimensionality, questions of this type. The point of that discussion that I gave is that to understand whether a model class is good is not simply a matter of understanding whether neural nets can approximate well the functions in the model class. In fact, there's a gap between how well you approximate and how well you do from data. This is now being enumerated in some papers. It's called the theory to practice gap. All right, so I've pushed model classes. I think when I talk to people doing deep learning, they don't typically use model classes and they argue against it. So what is their viewpoint? Their viewpoint is, well, we have an algorithm and we know our algorithm is great, right? We know this deep learning does a wonderful job. We can show you empirically in a lot of examples that it's doing well. We don't have a model class, but we somehow know that deep learning is picking out a certain function as how it takes the data and extends the function off of the data. and there are attempts to explain what that function is. You're probably familiar with neural tangent kernels for single layer networks, and people are trying to understand what is happening in deeper networks. So their view is that, well, we have a good algorithm. It wasn't that we started with a problem where we knew the model class, and now we'll create an algorithm depending on the model class. No, we forget the model class. We have the algorithm, and now we'll try to understand, in essence, which model class was lurking in the background that our numerical algorithm was actually finding. So this is a different view, and one thing that bothers me is that since they're using the same algorithm, no matter what the underlying model class was, that seems very strange to me. Seems to me different problems should indicate different learning algorithms. Now, they would argue that, well, we do that by changing the activation function, by changing the architecture, maybe changing learning rates, et cetera. But then it becomes sort of an art to figure out what the algorithm is. Okay.
I'm going to interrupt just a minute. We've got just about 3 or 4 minutes left before we have to move on.
Yeah, I'm going to move fast. Okay. Okay, so I'll do this in 1 minute. I said, okay, what functions are we learning when we use deep learning? So I said, let's take a simple example. Let's take the function x squared. I'll give you data at 100 equally spaced points on 0, 1. You tell me what function you generated. What is f hat when you use deep learning? I put it into TensorFlow. I get nonsense out. All right, I try TensorFlow, and the functions it gives me as the approximation to x squared are like constant functions or the zero function, and so this is very poor. And I know then I must be doing something wrong. I call Boris Hanin, say, what have I done wrong? He tells me various things that are the state of the art. That is, you have to really choose networks which are wide, and you have to use the slow learning rates and so on. So the point of this is that you can't just take an off-the-shelf algorithm for learning, throw in your problem, and walk away and come back and get a good fit. It doesn't work that way. After you do some, art work of designing the algorithm, you will get a reasonably good fit, but I don't see a theorem in the form that do this and I guarantee you that you will get a good fit with a certain accuracy. Okay, so I think I have 2 minutes. And in this 2 minutes, I want to turn to generalization error, which I alluded to already. And it's peculiar to me that this idea of generalization error has supplanted what mathematicians would usually like, which is a certified theorem that says, I guarantee you a certain error that is the norm of f minus f hat is small if you use my technology. Because this would be certifiability of a learning algorithm if you had an explicit error estimate. But instead, what's done in practice is one looks at the test data and, for example, looks at a square loss and says, okay, we train and we find that this loss is small. And so good, we have a good fit to our function f hat. Is this truly a good fit? What can you say in terms of certifiable performance? And the answer is, well, you can't say anything with certainty, right? Because the draws that you have of the data, as I mentioned, could be good draws or bad draws. Now, you may say, well, I'll say something in terms of expected error, that even though the quantity I've computed, I can't guarantee that the true error is bounded by this quantity or anything related to it, maybe I can say something about that with high probability on the draw that this would be the case. And if you go into that world, then the best you can say is that the error with high probability, the true error behaves like this, where m prime is the number of elements in the test set. So you could think of m prime as replaced by m. Notice the minus a half, which comes up from concentration of measure inequalities. And even though epsilon m may be very small, right? Much smaller than m to the minus 1/2, I'll never get a certification that I'm performing near optimally. Can I get 1 minute to finish this last slide, Greg?
All right, go ahead, and then we'll have to move on.
Yeah. So simple example, take the Barron class, dimension 1, it's the toy example. Approximation rate is n to the minus 2 if n is the number of parameters. Galfond width is m to the minus 2 when m is the number of data. Point wise Galfond width is m to the minus 3/2. Average Galfond width is m to the minus 3/2 log m. This would be, if I knew the model class, injected it into my algorithm, I should be able to get this rate. If I do generalization error, I'll only get this. I will never get close to the optimal performance. Bottom line, I don't see generalization error as a good concept to measure whether you are performing near optimal rate or giving you good guarantees on performance. Okay, I stopped there. I sorry that I took a minute over and that I sort of rushed through these last parts, but I'll stop at this point. Okay?
No problem. Thanks very much. If anyone who's willing, why don't you unmute just for a second and we'll give a round of applause here. Just unmute briefly and we'll give Ron a round of applause.
Okay, thank you.
Great, thanks very much. We don't really have time for questions, but maybe we can have some time later on to do some questions offline.
Okay, I'm going to stop screen.
Okay, here's the first talk, and then we're going to move on to...
Minlang, let me ask if Lulu or Shin is listening, if what DeVore saw in the functional approximation was a dying ReLU, right? His first attempt was basically because he had a narrow network, and we know from your work that basically he has a dying ReLU. So if he increased the width, that like
yes, yeah, he used a network of 10 layers and 3 neurons per layer. It's definitely a dying ReLU. Yeah.
Right. So it's a classical case of dying ReLU. So probably we should send him the paper. I'll send to him. Send me the final version. I can send to him.
Sure.
Because DeVore was actually supposed to be last year our Gottlieb Memorial lecture speaker, but because of course of the pandemic, we canceled it. So anyway, it's good that we listened to him. But he's always been a skeptic. He's of course a great thinker. So I hope you all enjoy this talk. Go ahead, Minlang, go ahead with the next talk. The next talk is on optimization. So today we look both at, because DeVore looked at approximation and generalization. The other big, of course, problem is optimization. So Jason Lee, who will give a talk, is a student of Michael Jordan, and it's all about this type of,
So our next speaker is Jason Lee from the Department of EECS at Princeton University. Here, the title is the Whirlwood Tour of Linearization and Beyond in Deep Learning. Let's welcome.
Today, I wanted to talk about some of the, give an overview of the work done in deep learning using this linearization tool and how you can go beyond linearization. Because what it can prove, what it cannot prove, and how to go further. So there are some subjective statements, and those are my opinion, but all of the mathematical statements are joint work. Okay, so I wanted to talk about a few topics. The first one is what is linearization in deep learning, how to go beyond this, more recent results in going beyond linearization, and sort of the open problems left. So I'll focus more about on what optimization-based algorithms, or mostly what gradient-based algorithms can prove for minimizing the train loss. So this means I will essentially not talk about methods such as spectral methods and tensor methods, which are also very efficient, give computationally efficient and statistically efficient methods for deep learning, simply because they kind of just don't fall well into the framework I'll use to think about things. Okay. So I'll categorize sort of proofs for gradient-based deep learning into 3 categories. The first one only uses that the gradient is non-vanishing. So this is like essentially gradient non-vanishing. By the descent lemma, you make progress. And if you keep making progress, you converge to a global minimizer. Perhaps one of the simplest proofs you could ever come up with. Okay. And then there are proofs that require some information in higher order derivatives, though the algorithms do not. For example, if you want to converge to local minimizers, then perhaps local minimizers have better statistical guarantees than simply stationary points. You can do this via gradient-based algorithms, although the algorithm doesn't need any Hessian information. And finally, I'll talk about sort of the third class is methods that require a sequential order of learning. They sort of need to argue that you first learn A, and then after you learn A, you can then learn B easily, and so forth. So let me give some examples to make this more concrete of these 3 categories of what we can learn with gradient methods. Category 1 essentially contains all of convex optimization. Convex optimization, like if you have the convex optimization, if gradient f of x is 0, implies global min. And then so the converse is, and then so of course, if the gradient is not 0, then you're not at a global min. So you can keep making progress until the gradient hits 0, which gradient descent will always hit 0 eventually. And then you must be a global min. So actually, so beyond convex optimization, there are a few interesting examples of where this gradient non-vanishing condition holds. Yet it's not convex. Among these are sort of these single neuron models, plus well specified. So the data comes from W star plus noise. And then if you do gradient descent on the square loss, let's say, then you will find W star, although it's not convex. This kind of things go by many names: 1-point convexity, star convexity, most of local convergence. You might have heard of things like the PL condition, KL condition. There's 1,000 things. They're all kind of the same. Quadratic growth. Okay. Unfortunately, this is pretty restrictive. All of these models essentially need just a unique global min, because, or at least a connected set of global min. For example, this would not allow you to do a matrix factorization in the rank 1 case even, because W and minus W could be both global minima, but they're not connected, and there's no way for something like the PL condition to hold in that case. So kind of motivated by this need to go beyond just looking at the gradient, category 2, people started looking at what happens if the gradient is 0 and the Hessian is PSD. So this is essentially local minima, informally speaking. And now you can talk about slightly more things. You can now have matrix factorization, matrix completion. So all of these matrix problems fall under this category, like SVDs, eigenvalue decompositions. Those are all non-convex problems. But you could argue one reason that they're efficiently computable is they have good landscape properties. And category 2 is really about these landscape properties. The topology, the geometry of the landscape. So then tensor decompositions also fall in this category. Phase retrieval, saddle points. You can massage two-layered networks with a carefully designed loss, not with a natural loss, into this category 2 of category 2 methods. Category 3, these are more specific methods. They require very specific assumptions on Y condition X. A lot of these argue sort of a hierarchical learning process. So I've given some references here. I'll discuss one of them, one of my own works, later on in the talk. And so category 3 proofs generally kind of look like chaining together of steps of category 1 and 2. And then you kind of alternate between using these and depending on which stage of the algorithm you're in and what you need to learn. Okay, so my plan for today is I'll try to cover using first order and second order information. I'll first talk about the linearization principle, and as it's sort of the most generally applicable, and then I'll move on to a little bit of things in category 2 and 3. Okay, so what is linearization in deep learning? This is nothing but Taylor's theorem. So you have, this is your network, just some nonlinear function of X. You Taylor series around your current point. This term will generally ignore, it can be bounded in, pretty simply, or just think about it as some order 1 quantity. This is the important term. And then for some reason, I'll throw away this term. More precisely, I should have wrote it like this. But it turns out that there are some simple scaling tricks you can do to make this very small. Little of 1 with respect to the width. I'll talk about this in a second. Okay, so then if the second term were negligible, then what we would have is that f theta is now linear in theta, right? This term here is linear in theta. And suddenly you've reduced deep learning to a linear function. And then if you can use overparameterization kind of to kill this and this one. And then now suddenly you've just got a linear function. The important thing is killing the second term. The first term is not dependent on theta, so it doesn't affect optimization anyway. So this technique was first used in one of my earlier works with Sota no Katabi and Javin Martin Lee to prove that gradient descent can find global minimum with minimal overparameterization. Later on, it was reinterpreted as sort of as this kernel viewpoint by Jacot and Du et al., Aurora, Shazad, and Bach, called the NTK. And then in parallel work, other groups of authors called it the pseudo network, but they're kind of the same thing, is that you just approximate the network with a linear function. And I'll show you the original proof from the Sota no Katabi et al. Paper of how this can get you to show you that gradient descent converges to a global minimizer. Okay. So you can think about this now. The reason sometimes this is called the neural tangent kernel is that it's just you think of that as a linear function and you think of this as the feature map. And then if you have any convex loss function or any loss function really, you can kernelize it and it's equivalent to solving a kernel machine with this kernel here. Okay, so we're not going to talk today much about kernel methods and the statistical properties of kernel methods. Instead, I'm going to focus on linearization mostly as a tool for analyzing optimization. So let me look at two-layer neural networks. I'm only going to train the W's for now. The loss will be convex. It will be square loss. However, this is non-convex in W's. You train the W's, they're on the inside of the nonlinearity. This is non-convex. It's convex in the A's, but non-convex in the W's. And then if you train both, it's non-convex still. Okay. But now look at this linearized guy. Now this is linear in theta. So linear function composed with any positive convex loss. That's a convex function theta. So actually, if I could magically optimize the linearized function instead of the neural net, I would have a convex optimization. In fact, it satisfies one of the conditions I mentioned. This is the Polyak condition. When the sigma min, the minimum singular value of the Jacobian is positive. So the Jacobian is a matrix that's parameters by n. It stacks the gradient with respect to theta of x1 through xn. Okay. And then, so I'll show you how we use this in our 2017 paper that I think first used this linearization, at least in the context of deep learning. Okay. So there's two steps you need to do here. The first is that you want to show that your linearized network f hat is close to theta for all the places GD goes. So this is obviously not globally true, right? Like as soon as you
allowed
the second term in the table theory dominates the first term, this is not true anymore. But the hope is that if you converge so fast that you don't need to move a lot, then this can be true. And in fact, the way you'll show you converge fast enough is by ensuring the Jacobian is positive, or the minimum singular value of the Jacobian is positive for all theta encountered by GD. Okay. The way we do this is by establishing two intermediate results. The first is showing that the Jacobian is sufficiently Lipschitz, which is equivalent to the Hessian being very small. This is essentially trivial, is essentially by a small rescaling trick. There's nothing deep here. And the second is showing that sigma min of J at initialization is positive via random matrix theory. This is difficult. Okay, and this is kind of trivial, essentially. To make the J sufficiently Lipschitz. And then finally, if you're sufficiently Lipschitz, just by Weyl inequality, the operator norm moves less than the Lipschitz constant. And then sigma min of J of theta is bigger than the initial one minus this. And then, so this is still positive. And then when this is positive, you converge geometrically. And because you converge geometrically, you don't move a lot, right? If you converge geometrically, it means your gradients are shrinking geometrically because the gradient norm is upper bounded by the loss. So then you must, and then so sort of you can just induct on this, right? You start out at a point where the sigma min is positive. So you take a gradient step that decreases the loss a lot. You moved a bit, still positive, you decrease the loss some more. And then eventually, because you're geometrically converging, the amount you can move is bounded O of 1. And then this is O of 1 also. But then you can use this rescaling trick to make this L very small. And that's essentially the heart of every NTK proof. Okay, so let's look at the Jacobian-Lipschitz lemma, and this is straightforward. This is just a calculation. And I did the calculation here for two-layer networks. You can do it for any depth. It's just backpropagation. There's nothing deep here. So it's the infinity norm of the derivative x Kronecker x is 2 norm. the infinity norm of the A's. Remember, my network looks like this. So you can see that this is roughly like, that looks like the Hessian, right? Because if I took two derivatives of this with respect to W, I get something that looks like this on the blocks. And then the Jacobian is the derivative of the Jacobian, which is the Lipschitz, is just the Hessian. You can see this looks exactly like the norm of the Hessian, right? You have X Kronecker X, that's this. There's A's here. And then, sorry, there's missing a prime here. And W minus W bar up here, that's the movement. And this is a deterministic lemma. Like I said, it just follows from backpropagation equations. And the rescaling trick is just to make these very small. In what is now called NTK parameterization, if you just set these to 1 over root m, it becomes very Lipschitz as m goes to infinity. And now the deeper result that allows you to do this with minimal overparameterization is this. Okay, so now you need to lower bound the minimum singular value of the Jacobian. And this needs randomness of the data. So we assume that the data is ID Gaussian and the number of neurons is bigger than the dimension. This is usually true in practice, especially when you're talking about overparameterization. So the Jacobian minimum singular value is D times the sigma min of the initial W0 times the A infinity norm. Okay. So if you can put this together, what this paper guarantees, this theorem guarantees, is that if you have Gaussian data, truly the minimal overparameterization, right? M times D is just the number of trainable parameters. It's like MD bigger than N log N or something. And M is bigger than D. You use any full rank initialization, you decrease the loss to 0. And of course, if you decrease the loss to 0, you found the global min. And the proof is just like the circular reasoning almost. You don't actually construct the global min anywhere. You just show the loss goes to 0 very fast because the sigma min is positive. And then because the sigma min is positive, WT stays near W0. And these together imply the existence of a global min near W0. The width we have is in fact sharp up to polylog factors. And fairly recently, Zhang and Montanari proved sort of the other direction here. When M is less than D and MD bigger than N, and W0 is random, they proved also a similar sigma min lemma, something similar to this. It's not exactly the same, but it suffices to get this theorem. So combining these, really, you can remove this condition here, that M bigger than D, if you combine it with their work here. But they need random initialization. So you, instead of full rank, you can just initialize W0 randomly, which is done in practice anyway. So sort of these two results combine really for two-layer networks to give a very complete story under the minimal overparameterization, gradient descent with this NTK rescaling trick. Converge decreases the loss to 0, although it's non-convex. Okay.
So one comment here.
This older result actually to the more recent NTK paper.
Can I make one comment here? So
Sure, go ahead.
in the one of the slides, Jason shows the smallest singular value part. So that is the one of the property that I use to show that the adaptive activation function actually helps to guarantee the strict positiveness of the smallest eigenvalue so that we can avoid that overparameterization in place of adaptive activation function. So that is the one of the core property that I used in the proof of the Kronecker network paper in the light of showing that use of the adaptive activation function helps in the sense of improving that the relax of the condition on the minimum singular value. I'm not sure whether George
Young-Sean,
is here.
did you make
Yeah.
this connection in the paper? Did you make this connection with Jason's theorem and the new theorem by Zhang and Montalinari?
Yes, I just make a comment that comparing to the standard theorem, which requires the number of neurons to grow at least m squared and more, and comparing their result, because of the use of the adaptive activation function, we don't really require the over-parameterization, and just order m is suffice. So I just make a quick comment on it. On the paper.
You may want to send him the paper, make the point, make that point. Send him the paper.
To Jason?
Yeah.
Yeah, might be good idea, but he can quickly get the idea because yeah, sure.
Just point to that. Yeah. Milan, go on.
And you'll notice that the width is essentially it depends on n in the weakest way, right? It's linear in the width. It's actually it's sublinear. It's actually n over d. Compared to like the papers following, usually you would need m bigger than a polynomial of n, very large polynomials, at least n squared, from what I remember. So it's kind of the what you gain here is because you were able to prove a bound on this Jacobian at W0, and you used a little bit more heavyweight random matrix theory compared to the more recent NTK papers, which kind of just use data separation conditions. So kind of you're leveraging here the Gaussian data. So also you note that sort of the optimization and the random matrix theory part is very separated. So any data set in which you can give a quantitative bound on sigma min, this theorem would apply. So I could equivalently change this theorem to if sigma min of Jacobian of theta 0 is bigger than something, then this holds true. So everything reduces to proving a lower bound on the minimum singular value of the Jacobian. So in fact, here we did not establish that the behavior is approximating the infinite width kernel. So we did not prove that the Jacobian is converging to the NTK kernel, which is defined to be like expectation sigma prime wx sigma prime w bar dot x. You're not converging to this quantity necessarily, and nor do you need this. This is something too stringent to desire if your only goal is to prove optimization results. And the finite width kernel in this linear regime is not close to the infinite width. There's no convergence in the operator kernel, for example. If there were a convergence operator norm, you would have a minimum lower bound on the singular value just by Wales inequality. And that's what these more recent papers do. But then you would need at least m bigger than n squared or something to get operator norm convergence. And here it's key that to do a sublinear in n, you really do need to leverage the fact that you can lower bound the Jacobian without proving a convergence of the kernel. Okay. So that's kind of what I wanted to say about linearization. And now I want to move on to a slightly different question to motivate why linearization is not enough for what we desire. So at the end of the day, we are concerned with statistical learning, not necessarily with optimization. Optimization was sort of just an intermediate challenge in achieving good learning, good statistical behavior in an efficient fashion. So now let's turn to the statistical question. This is kind of considered one of the most natural questions in deep learning theory. So take that you have a teacher network, let's say a 2-layer to be simple. And given data from this 2-layer network, I want to learn to accuracy epsilon. How many samples do I need and how much time do I need? So let's look at some potential results. So sort of here, the information theoretic sample complexity is n proportional to dr, which you can attain by brute force search. You essentially search over all A's and W's, throw down your epsilon net, compute the loss in the epsilon net, and keep the smallest one. And that will get you something like dr here. Of course, that's exponential time in both d and r. No one's ever going to use this algorithm. It's kind of just only for proof purposes, really. So a very, very, very good result, if you can do it computationally efficiently, would be like poly and D and R. Okay. So now let's look at a simple case. If the activation were a monomial or polynomial, you could do this with a polynomial kernel in D to the degree of the activation times some poly R factors. And this is sort of what NTK would do. NTK's behavior essentially is the same as that of a polynomial kernel. It's not too much difference. Okay, but then let's look at what is known sort of from the lower bounds side of things. So there's a lot of lower bounds for discrete distributions. These results kind of rule out any algorithm that do not use distributional assumptions or assumptions on W star that learn in poly DR, and probably even like D to the little of R probably is even hard. I didn't check very carefully. Okay, so the reason these are hard is if you could solve this teacher network problem, even the two-layer one, you can do things like learning intersection of half spaces, decision trees, juntas, many things that for a long time the learning theory community and the TCS community have considered to be somewhat intractable problems. And more recently, in the last year or 2 years, last year I think, there's even lower bounds if P of X is isotropic. So based on statistical queries, Diaco-Nicholas and also another paper by Goel showed something like you need D to the R queries, right? So that's kind of saying the kernel, this is like kind of pretty terrible. Is like, we wanted D to the R is something, it's something not very good. Of course, we shouldn't be scared off by lower bounds as long as we have good solid algorithmic ideas. And in fact, there are known cases of where there are algorithms that can actually solve this teacher network problem in the two-layer case through parameter recovery. So they solve something harder than the learning problem. For example, spectral methods pioneered by this paper of Janzemin, Zhang et al., they can learn teacher networks if R is less than equal to D and the sigma min of W star is positive. So in these constructions, sigma min is very close to 0 in these lower bound constructions. And in fact, you can do this even with SGD. This was done in a paper by myself, Rong Ge and Tenyu Ma, and then in the orthogonal case by Yuanzi Li and Tenyu Ma. They show SGD can estimate parameters, but under even stronger assumptions. Like they need this plus some positivity on the coefficients. Okay. So sort of how can we go beyond this with methods that are computationally efficient and try to get statistical efficiency, but perhaps without sort of these condition number assumptions. And now let's turn to sort of a functional analysis viewpoint. This is very related to what Andrea discussed in his talk using LP norms. Let's look at two function spaces that are kind of quote unquote natural in this case, in the two-layer teacher net problem. You can define f star of x again as a teacher network, and we will write as an integral with respect to a measure rho. And then this rho will be just delta functions in the case that, so just delta at wj with aj outside in this case. So if I want to represent a finite teacher network, I just write it as as an integral of Dirac delta functions which is of course equivalent to just a sum of neurons. And the features, this is sort of the natural featureization if you have a two-layer network. But what's very, very important here is the norm in which you measure your row, which give you different function spaces. There's two kind of what I would call natural spaces. The first one I will call F2 of B. It's a Hilbert space. It's in fact an RHS. And it's also an NTK. It's the NTK with respect to the last layer parameters, the A's. So that's, I don't know who first discovered this, at least as old as Radford Neal, Rahimi Rack, Cho, and Sol, studied for at least 20 years now. So it's well known that you can have these kernels like that are loosely induced or motivated by neural nets, but their behavior is not like that of neural nets in terms of statistical or computational, really. The second one is F1 of B. It's a Banach space. It's sometimes called convex neural nets, proposed by Bengio, Bach later studies. Many authors have studied this. And F1 of B is kind of nice because if you believe your teacher network is kind of small, then L1 norms give sparsity. And that's kind of why you would kind of think that F1 of B may have better statistical properties. And this would be correct. So the global, if you use weight decay on a two-layer network, in fact, the global minimum of the loss plus weight decay is given by F1, is the minimum F1 norm solution. Sort of mean field approaches are naturally lie around F1, and a lot of the work on implicit regularization by myself, Shizat Bach, Kai-Feng Liu, Colin Wei, all of this is sort of looking at F1 and its sort of statistical properties. So why do we like F1? If you are a statistician that doesn't care about computation, F1 has all of the magical properties you would desire. The sample size is proportional to the F1 norm squared over epsilon squared, and the F1 norm is adaptive to lower dimensional structure. Meaning if f star of x were some polynomial of ux and u just chooses r of the coordinates or r dimensional subspace, and this p is degree q, you only pay exponential in r to the q, right? You don't pay d to the q. A kernel method would pay d to the q. It just essentially ignores the fact that it's low dimensional. Even better, if you had a ReLU teacher net or sigmoid teacher net, it doesn't really matter. The sample complexity is d poly r for a reasonably small polynomial, like r squared or something. And this is easy to find by like Rademacher complexity. Okay. However, if you're concerned with computation like me, then this F1 space is really a red herring, a distraction. F1 almost certainly cannot be efficiently learned since it includes all two-layer teacher networks of width R. So sort of all of the previous lower bounds apply to F1. And sort of thinking in this abstract functional analysis viewpoint or mean field viewpoint, it is very hard to leverage any data structure either in P of X or Y condition on X. So it's kind of unlikely that mean field or any SGD approach really, or any algorithm really, will yield polynomial time learning for all of F1. So now let's turn to F2. F2 is great if you like computation. It can be learned via SGD. It's a kernel method. It can be learned by matrix inversion since it's a kernel method. However, it has terrible, terrible statistical properties. It completely ignores low dimensional structure. Just as an example, if you depend only on one coordinate, like the function W or U what's my notation here? U transpose X to the Qth power would need you D to the Q samples instead of D samples. Okay, this is terrible. F1 needed D samples, you pay D to the Q, although you only depend on one direction. like a teacher network with a single ReLU has something like exponential, actually probably infinite F2 norm. But if you truncate, willing to tolerate some inaccuracy, it's something like exponential D over epsilon squared. And your sample complexity, the best result really I know of is something like D to the 1 over epsilon to some power. And as far as statistical results go, F2 and NTK all behave similarly. All of my comments here apply to NTK also. Is that NTK sort of just ignore low dimensional structure. Okay, so the goal you really want to do is try to find the sweet spot. You want to find an in-between space that adapts to low dimensional structure and is computationally efficient, preferably via SGD. So, the obvious guess when I thought about this a year or two ago is LP norms. And Andrea luckily discussed it this morning, and as he told us, it's very, very hard to use sort of random features plus LP regression on top of the random features for P equals 1. Like you would need an exponential number of random features to get close to 1. And LP for like P equal 1.1 for some constant P, like you really need P equals like 1 plus 1 over D or something to get the statistical properties of the L1 norm. But this would be you would need exponential and D random features. So something like L1.1 would not get any of these low dimensional benefits of F1 I talked about. So kind of I think this is the natural thing that the first thing anyone would think of is to look at LP. But as far as I can tell, it won't lead to tractable algorithms. So let's turn instead to a different motivation. Things we do, we should always, if you're looking at computation, you should always look at things that we know how to solve and build on top of those, instead of starting with like abstract function spaces. So let's look at what we do know how to learn very well, quadratic activations. Okay, so quadratic activations, you can write again as this in this integral form to make an analogy. F2 then gives you a Frobenius norm inductive bias. F1 gives you a nuclear norm inductive bias. This is very good. Okay, this is everything we know about low rank, low dimensional. This is kind of bad. Okay, luckily, the reason I wanted to start with quadratic activation is, in fact, in this special case, F1 is learnable. So it kind of suggests that rank is a reasonable measure of low dimensional latent structure. And if you have monomial activations, the rank of the tensor does exactly correspond to the width of the network. So I will define this function class I call low rank polynomials. And this is the definition. You can think of it, it's like teacher network where all of the activations are monomials or polynomials with normalizations to make everything make sense. Okay, so this is an interesting class because you include teacher networks with polynomial activation of bounded degree, even analytic degree approximately. You can truncate analytic activations to log 1 over epsilon degree. Constant depth teacher networks with polynomial activation. It blows up exponentially in the depth, but as long as the depth is constant, it's still in this class with polynomial R. And the real reason is I can show you a non-trivial learning guarantee with SGD that's not attainable via kernel methods. Or in fact, not attainable except without pretty sophisticated methods. So let's look at what our baseline approaches do. F2 needs D to the P samples. They kind of just, this is the same thing with all kernels. They just ignore low dimensional structure. And you just get D to the power of the poly degree. F1 is D to the poly R. It's essentially optimal. Of course, the issue is it's exponential time. We don't know how to learn this efficiently. And one of my earlier works with U-Bi, you can learn this with a very, very modest improvement over the kernel. D to the P improves to D to the P minus 1. Okay, so a tiny, tiny improvement, but at least it shows that you can beat D to the P with a computationally efficient algorithm also. So of course, there's still a huge gap here, right? This is the gap here. There's a lot to close here. And in fact, what I will show you today is SGD plus sign dropout, so I need to modify SGD a little bit, on a 3-layer architecture learns with n to the d to the p over 2. Sorry, this polynomial width, I mean, the width is actually d to the p over 2. So I need to, I need d to the p over 2 samples, and in time n poly d are p1 over epsilon and m. Okay, and the data assumptions are mildish. There's some moment assumptions you need. Things like, you essentially need like, how to say this? Like the moments of X tensor P over 2 behave like those of a Gaussian or any multivariate Gaussian. So any multivariate Gaussian with any covariance of bounded condition number, elliptical distributions on spheres, these are all fine. But it's not just tail assumptions. You do need things about the shape, the moments up to a pretty high degree. Okay. So the architecture, so then the running time, essentially, you should think the sample complexity is d to the p over 2, the width is d to the p over 2, and the running time is linear in the n. Actually, it's linear in the n, linear in the m, and polynomial in the other things. Okay. So what is the architecture? And then in analogy to Daniel's talk, you should think, okay, this d to the p over 2 should really remind you of his complexity result about learning tensors of order p, and they also need d to the p over 2. And that's kind of what's happening here under the hood, is that this 3-layer neural net architecture is simulating matricization, which is one of the techniques Daniel discussed. One of the simplest ways to learn an order p tensor with d to the p over 2 samples is to reshape it in a matrix of d to the p over 2 by d to the p over 2, and then do something like an SVD. So that's for like tensor decomposition or tensor completion. Our problem, very, very loosely, is kind of like tensor sensing. And that's kind of what's happening under the hood, is that we're going to use a 3-layer network that's implicitly doing a form of matricization. At least in the proof, we're using matricization. So we will only train WR, and we'll fix the ARs, A's and B's at random initialization. You can train them, but we don't know how to prove training them helps. But we do need them at random initialization. There's a lower bound if you only have a 2-layer network. Although it's not a very strong lower bound, so I won't even discuss it. But as far as I know, a 3-layer network is essential. You want to build a sort of a quadratic random feature set on top of a ReLU random feature set. So what is the algorithm? Algorithm is, first you want to estimate the covariance of the random features from the first layer. That's these G's. You form this sigma hat. You use the sigma hat as a weighted regularizer. This is some weird norm. It's not very important. The point is, it needs to be something like close to a 2 infinity norm, which is like every row cannot be too big. And that's for proof purposes. If you prefer, you can think of it as Frobenius norm, and morally it's still true. And then you run SGD with a modification of dropout is, instead of 0, 1, use plus minus 1. This prevents anti-Hay behavior from happening and lets you use much bigger learning rates. So kind of the reason this works is that, let me sketch the reason it works. If I knew the input were Gaussian, and I choose the G's to be Hermit polynomials instead of ReLUs, this makes the proof very easy to see, very intuitive if you think of Hermit polynomials. If you initialize this many Hermit polynomials, you can get a basis of degree p over 2 polynomials. Then you can express any beta dot x to p over 2 as linear in the Hermits. And then these go into the next layer, the final hidden layer. And the final hidden layer is going to vary something similar. It's going to just learn to square these guys, which you should think of as quadratic activations. So sort of the one thing we know, the one like thing that universally we know how to do computationally efficiently and statistically efficiently is quadratic activations, matrix sensing. And this needs almost no assumptions on data. So we're very, very good at learning quadratic activations of the input, even with random feature, like a random featureized version of matrix sensing. So you can think of this as random features, but now it's not RKHS, it's sort of a nuclear norm random features. And that allows you to get statistical benefits. And this allows you to be universal. So you don't need, like, the problem with just matrices is that you're not universal. You can only learn degree 2. Now you're universal. You've learned to square Hermite polynomials of degree p over 2. So that lets you learn anything of degree p. So that lets you learn anything of this form. And if you have multiple of these, you just use different neurons to do this. So that lets you learn anything of this form here. Oops, this should be R. And that's essentially how this works, is that in the first hidden layer, you try to mimic a basis of Hermite polynomials if it were Gaussian. And then the second layer learns to square them. Sort of in the non-Gaussian case, you just learn something like an approximate basis of degree p over 2. I don't know what the basis is. If it's not Gaussian, it doesn't matter. It's approximately a basis. And then the second layer, I learned how to square it, but then the squaring is very statistically efficient. So there's several potential improvements. Something that I think is probably within reach is if you train the first hidden layer, the V's, you can improve the epsilon dependence by sort of a fine-tuning, like a feature learning argument. Because right now you're paying an extra 1 over epsilon squared is because you're only epsilon approximating. The hope is like if you fine-tune it, you can get rid of these epsilons. Although even this, I think, is technically not that easy. Anyway, it's not a very big improvement. The bigger question, is poly D possible? And we already heard from Daniel that there's very likely it's not possible. That D to the P over 2 is kind of, for many reasons, is a fundamental limit in tensor completion and sensing. And our family of low-rank polynomials includes tensor completion, tensor sensing. SOS can only get D to the P over 2. Daniel showed some unconditional lower bounds today that indicate D to the P over 2. Okay, so of course, never be deterred by lower bounds. It just means we need better assumptions. What is let's move on to hierarchical models. For example, deeper things. Low-rank polynomials are very good for constant depth or depth 2. Perhaps we can learn things where we chain together low-rank polynomials and then their functions of them. So this would be very nice because then you can start to talk about deep networks. And here's like sort of perhaps one that might be easier, like a ResNet-ish form of it. And this you might think is easier because you have some direct signal from the feature map. I still don't know how to prove this, but it seems maybe plausible. And sort of the big picture questions is trying to attain a systematic understanding of what is computationally possible via SGD. Like, what are the things we can learn beyond kernel methods? Right now, it's fairly limited. Like I said, the only thing that's really general and completely agnostic to data assumptions is sort of these quadratic NTKs, which we exploited with a 3-layer architecture. But what else can we exploit? And then what are the things that can use assumptions on Y conditional on X and assumptions on P of X? Really, P of X assumptions are not heavily used in any SGD analysis that I know of. Y conditional X are sometimes used in these category 3 proofs, but they're pretty fragile. You need pretty specific data assumptions. And how will these interact with architecture, algorithm, regularization? How will this interact to learn good representations, not only classification? So the big win in deep learning is not just classifying well with our samples, it's that by classifying well, it also learns good representations. we have a pretty good understanding now statistically how this happens, but we have virtually no work on learning good representations beyond the linear case. That's sort of all I wanted to say. Thank you for listening.
Thank you very much for a very nice talk. Any question from the audience? Please feel free to unmute yourself or raise your hand. Jason, can I ask you a question about the
Yes.
the linearization? Where you mentioned that in your early work you require that the width is sublinear in terms of data samples, and in the NTK papers they require like at least quadratic, right?
Yeah, it's quadratic. I think the best you can do is quadratic.
Yeah. So could you explain the intuition why you can get better rate like sublinear?
Yeah, it's because in the NTK papers we took a little bit of a not intelligent route to this at some level. Is what kind of the arguments, if you look at my papers as Simon Do, for example, is we had the Jacobian, I'll just use Jacobian. We use Jacobian transpose Jacobian. The infinite width one, and then the finite width one. And we kind of just proved that this is small. Something. But to get operator norm convergence, I think you need at least superlinear. I don't actually know. I think Andrea knows, but I think if it's not, I think it's at least n squared. It's definitely not linear. Like I know for a fact if it's m equal n over d, it's not true. You don't get operator norm convergence. So sort of the early papers here, they just use something like a matrix Bernstein, matrix Hufting, and you get some n to some c over root m. So you got something like this. And then once you get this, you know this is positive. The sigma min of this guy is positive. And then you just, so then sigma min by Weyls inequality, this is bigger than this guy minus nc over root m. So you kind of combine these two and you get something like poly n. And that's essentially what all of the NTK papers do.
Yeah.
Is sort of, they kind of avoid doing random matrix theory because now all you need to do is matrix Bernstein. You don't need to, the harder thing, the thing you should have done is directly analyze this minimum singular value, which is much harder.
Yeah. So
of course, you need Gaussian, you need data assumptions. Like Gaussian's not necessary, but like you definitely need something like, very high moments look like Gaussian. Like something you need something like the convex Lipschitz concentration to apply. That's sort of like the main thing you need.
Yeah. Can I ask another follow-up question in this direction? So in the literature, do you know any paper studying the propagation of this Gaussian randomness around the iteration? Because the Gaussian randomness is the crucial assumption in proving the sigma mean is positive. And I think the key to prove global convergence is to prove that the sigma mean is always positive, as you mentioned in your talk. So is it possible to analyze propagation of the randomness around the iteration to prove that without linearization, or we can prove that sigma mean is positive?
Not that I know of. The only way I know is to prove that you don't move a lot from the initialization.
So how you move it's still unknown.
Yeah, like for example, if you train this, let's say you add regularization, like weight decay, then you would move a lot, or you use logistic loss, so you would move a lot. And then how does sigma min of the Jacobian change? I have no idea. That, like, if you could prove a lower bound, you could basically, is this true? Sorry, let me think. If you could always guarantee to me sigma min of j is positive everywhere, or everywhere gradient descent went, or SGD went, yes, then you could solve all of the F1 things. Yeah, that's true. That's something we proved in a paper with Colin Way and Tang. Yeah, so like this is, it's probably impossible. Like you would need, I don't know what you would need. It would have to be data assumptions.
Sure.
But sort of, it's very hard to see data assumptions at this abstraction level. So it's probably not the right way to go about it.
I see. Thanks.
Yeah.
Any more questions from the audience? So if we don't have more questions, let's thank Jason again.
Okay, so any comments from our audience here?
If Handi is listening, or Shin, the LP norms look interesting, but I'll discuss this with them. Well, okay, so a lot of people dropped out because of the theoretical part, but I think it's important to see that there is, people are sort of thinking. I hope everybody understood the first part, the linear part, how this, the NTK, because that's fundamental. The second part is trying to find different norms, go beyond the linearization that he talked about, which is, but if you combine the two parts, right, the first part, the first talk and the second talk, you will see that over-parameterization has an effect both on the generalization as well as on the optimization. So when you design your networks, you actually have to think about that. How much data is there and what is the size of the network, okay? So don't just randomly throw numbers at it. So that's why I think it could be useful for everybody, not just the people who do theory, but also the practitioners, to know a little more, like this mistake that DeVore did. That's a rookie mistake. So you should try to avoid that. And of course, the paper of Shin and Lulu show that you cannot have, when you go deeper, you also have to go wider, certainly for the ReLU networks. So that's where ReLU they can analyze. But maybe in Milan we can stop here, and next time we'll have live speakers again.
Right. That's the announcement that I would like to make. Thanks everybody for tuning in. So everybody have a good weekend and take care. Bye-bye.